that the pipes need to fit together, you need those diameters to have literally, like, you need to make sure that the machine is working so that the diameters have barely any change, like barely any, because what would happen is the pipes wouldn't fit, correct? So you need to check for the variances, which are the changes in the diameters. You need to check for the standard deviation. So that's where you would actually use a confidence interval. You want to make sure that your diameters are super, super connected and tight. So that's what they would look for. And what we use for variances for confidence intervals and standard deviation is this thing called chi, not chi, chi-square distribution. Remember, everything in mathematics is usually based off of the Greek alphabet. And chi looks like this. It's this, like a curly X, but it's called chi-square. So you put a little 2. Chi-square distribution. I do want you to write down the characteristics of the chi-square distribution, because these are a little bit different than what we've been dealing with in our normal curve. So all chi-square values are greater than or equal to 0. All of the chi-square values are greater than or equal to 0. Sounds good. No negatives. Another characteristic of the chi-square distribution is that it is a family of curves based on degrees of freedom. And again, we know what degrees of freedom are. Anybody want to refresh me on what degrees of freedom are? N minus 1. You just take however many things there are in your sample and take away 1, okay? The area under that curve is going to equal 1 or 100%. So that is something that we're familiar with. Now, this is the new thing that's really weird about variances and standard deviations and the distribution of them. The chi-square distribution are right skewed. They are always, always, always positive. They're positively skewed. And you can see it from the sheet that I've given you, okay? Chi-square is always, always like right skewed. So the more of the data will be all to the right. And again, you could have, it's a family of curves, so you could have your data like that, but it would still be more right skewed, okay? Whereas we're used to looking at distributions where the hump is in the middle. That's a normal distribution. This is a chi-square distribution. It's going to be positively right skewed. Now, what you're supposed to then do, and I'm going to show you the trick because I'm just a nice person. You have to, let's say I want a 90% interval. So I want from there to there, okay? The 90% area. You would need to find this guy on the left, this chi-squared value on the left, and this guy on the right. Okay, and it's based off of degrees of freedom. So again, you would have 0.05 here and 0.05 here, and we always read from left to right. So how much is that? Point what? 0.95. Okay, so you actually have to read 0.95 on the chart. And then this guy would be what's called, this would be chi-square right, and this would be your chi-square left value. So here's how we're going to do it. And I should have given this to you on a white piece of paper so you can actually block it out. But if you have a 90% distribution, I kind of wrote it on here, but this is terrible. You are going to block out the 95% column, 0.95, and the 0.05. And this is where you'll get your two values. You do the 0.95 and the 0.05. That would be for you want to be confident at 90%. You would use this one for your left, chi-squared, and this one for your right. This one for your left and right, left and right, left and right, left and right, okay? If you want a chi-square and be confident 95% of the time, well, that would be this column. And again, I'm sorry, I chose to do yellow. I should have done, I don't know if you want to use a highlighter or whatever. This is the 95% confident one. If you need other colors, I can give them to you. Yeah. You need other colors? The 99%, you don't want to actually choose this one and this one because 99%, remember, would have 0.01 on either side, which you would have to cut in half. So you actually choose this first one. And then this last one. I'm sure it's on the calculator. I think I've found it before, but I don't remember it. To be honest with you, it's just so much easier looking at this chart to find those two numbers, okay? I know it doesn't seem that way, but it actually is much easier to find these two numbers on the chart, okay? So if you want 99%, you would do this first one and this last one. If you want 95%, skip a row. 95% would be 0.975 to 0.025, and then 90% would be the 0.95 to 0.05. And that's again because right here, look, you're actually going 0.95% when you do 90%. So I know it seems awkward because you're like, can't I just go to the 90% for 90%? No, no. We're doing a confidence interval, so we're doing the middle 90%, okay? So the first part of the worksheet that I given to you, anybody need another color or need something? You could use a highlighter, however you want to do this, is take out this sheet. It says, use the chart to find the values for chi-squared right and chi-squared left for each of the following. A 90% confidence when n is 25. So the first thing you need to do is degrees of freedom. What would be the degrees of freedom if you had 25? 24. 90% confidence. Okay, so that means I go to 24 on my yellow sheet, which is right there. And then I want to look at the 90%. You see my fingers right here? I don't pick that first box. Second, I look at 13.84. And what's the other one that matches it? Yep, 13.848. And chi-squared right would be 36.415. See, I think that was much easier doing than if I had shown you how to do it in the calculator. All right, I want you to try 2 and 3 right now. Find the 99% confidence for n being 20. And find the 95% confidence for n being 15. So really all you have to do is degrees of freedom, look at the chart. Degrees of freedom, look at the chart. Pick the two values on the left and the right, left and right. For when n is 20, degree of freedom, what are you going to look at? 19, okay? Go to my yellow chart. I'm going to the 99% confidence, which is this first box, right? And the last box, God bless you. Go to 19, I kind of put my little line right here. What two numbers am I going to use then? 6.844 is your left, right? The bigger number is 38.582. Good, I'm glad you said that because my eye kind of went to the wrong one. Is that what you got? Easy, right? Hopefully not too hard. 95% when n is 15, so degrees of freedom, 14. Go to 95%, which for me is this like brown box, which is actually, I think, purple. Go to 14, line it up. Don't go to my green box, go to my brown box. 5.629 and 26.119. 5.629, 26.119. Now, how did they find this out? I mean, there's a way to obviously, there's a formula to find these chi-squareds out, but why? Why, when the table has it for you? Why do you want to do that? Just let the table do all the work kind of thing, okay? Is that hard right now? That's going to be the first part of your homework that you'll actually have to find this. And now for the formula. Are you ready for the formula? Don't you think these guys are going to be in the formula? And sad to tell you, this formula is not a magical one button in the calculator. So you actually have to do the work. It's okay. You can do it. Yours brilliant. Okay, here it is. N minus 1 times s squared over chi-squared right, which seems weird, but the right is on the left, less than the standard deviation squared, which is less than n minus 1 times s squared over chi-squared on the left. And minus 1 is also your, what is that called? Degrees of freedom. What does S stand for? Sample standard deviation. Okay? And what is this squared called when you square it? That's called the, look right above it, variance, when you square. So if they're asking, they're going to ask for two things today. They're going to say, find the confidence interval for the variance. That's what you do right there. So then what would be the formula to find for the standard deviation? What do you think would be the only thing? We square root it. That's right. Good job, y'all. Good job, Jack. I heard you. N minus 1 s squared divided by chi-squared right is less than just sigma, which is less than n minus 1 s squared over chi-squared left. Now again, why are we dividing by the higher number on the left side? Because that's exactly what will happen. When you divide by a higher number, you have a smaller number. I mean, think about it. You start dividing by 10, start dividing by 100, you get a smaller number. So that's why you want the bigger number on the right. So now we're going to do these two examples. It's really easy. I mean, you just actually find the one, and then you can always find the other one just by taking square root. It's not that bad. So I don't want you to kind of freak out. All right, here we go. Example 1, and then we'll do example 2, and we'll be done. A study on osteoporosis. It kind of got cut off, so I don't know why. Study on osteoporosis of 30 women found that the standard deviation of their ages was 5.2. Find the 95% confidence interval of the variance for their age variable. Assume the variable is normally distributed, meaning it's going to have, we can do our chi-squared because we're finding it for variance. All right, so a couple things in the story. We need an n. Look at the formula. What's our n? 30. What is our s? What is our sample standard deviation? I think it told us. 5.2. We need a chi-square right. We need a chi-square left. And it's based off of 95%. So if somebody would mind looking at the 95% and tell me what, and by the way, are we looking at 30? We're looking at 29, which is your degree of freedom. 16.047, correct? And what's the right?
45.72.
You got it. Okay. Take these wonderful numbers and plug them into that top formula. So the top formula is n minus 1, or really degrees of freedom, which is 29, times your s squared, just the s squared, divided by the chi-squared right number, 45.722. Then do 29 times 5.2 squared divided by the left. Again, I know it seems weird, but the bigger number is always on the left side because you want to divide by a high number. Now, when you put this into your calculator, again, whoops, sorry about that. Be really careful. I would do it, I mean, some of you do fractions really well, very easily here, but I would just do 29 times, I would put a parentheses and put 5.2 squared and hit enter, and then I would divide it by 45.722. And I get, I know it's hard to see with my 17.15. And then I see how I already have the 29.5152 squared answer up there. So I take that answer again. I don't know if you can see it. Let me try to. See how I already have that right there? So I arrow up to it. I hit enter, and now I divide it by the other chi-square, 16.047, and I get 48.867, 48.87. Let's say they had asked for the confidence interval for standard deviation. Guess what you would just do with these two numbers? Guess what you would do? Just square root them. Don't go back to a new formula. Just take the square root of these. So let's just do that just for fun. So what's the square root of the 17 guy? And I get 4.14. And square root the 48 guy. 6.99.
Wait, so do we have to do that?
No, I just wanted to show you if they did ask for it. So this is my interval for variance. This is my confidence interval for variance. This would be my confidence intervals for if they did ask me standard deviation. Okay.
And
Do you have to write sentences? Since you're doing this formula and you have to do it by hand because it's not in the calculator, you don't have to write sentences. But your sentences would be pretty much the same thing. I am 95% confident that the variance for osteoporosis women is between 17 and 48. That's it. Yes, sir.
So when you put the two numbers, you have to put the standard deviation in the middle, or you just put the comma between what we used to?
You put this, you can put the comma, by the way, for the interval. But the problem is when you do this, then I know it's for variance. Do you see what I'm saying? Like if you put the comma there, you might be like thinking that it's mean. Like this is not talking about their ages, right? 17 is not their age. 17 is the change in their age. It's like a 17 years to 48 year. That's the variability of women with osteoporosis. So you could, totally fine, but I'll be okay with either right now. I just want to make sure you know how to do that. All right, one more, we're done. This one's a little different because notice they've given you some data here. So you actually have to go back and do something that you should be familiar with. Find the 90% confidence interval for the variance and standard deviation for the number of named storms per year in the Atlantic Basin. A random sample of 10 years has been used. Assume the distribution is approximately normal. How many things do I have? How many storms do I have? 10. What would be my degrees of freedom then? 9. I need a standard deviation, and then I need a chi-squared left and a chi-square right. We can do the chi-square left and right real quick because that's not hard. This is based off of 90%. Go to your yellow sheet right here. 90%, we would go to degree of freedom 9. So 3.325 and 16.9.1. 3.325, 16.919. Guys, how are we going to get a standard deviation for this sample? You should know this. Where do we always go? L1. Let's go there. Stat, edit. I'm going to just clear these out. Clear, edit. Go to L1 and start typing these 10 things. Oh, it keeps doing that. 11, 14, 13, 16. How do we find standard deviation in our calculator? Do you remember? Stat, edit. I'm just writing this down for those who don't remember. L1. And then you go to stat, calc. Remember, it's called 1 vars. Okay. Let's go to stat, calc, 1 vars. I'm going to change my list. Enter, enter. Which one do I use? Which one do I use? SX is your sample standard deviation. I have 4.1, so I'm going to go 4.1. Okay? And now I'm going to put it into my formula above. My formula, and I always start with variance. So my formula says n minus 1, so that's degrees of freedom, 9, times my standard deviation squared, divided by my chi-squared right, which is the larger number. Do the same thing on the left, except divide by your chi-squared left. Find the standard deviation to these two numbers? Square root. And what'd you get there since mines are off?
6.75.
6.75 and
2.99.
2.99. So, I mean, I don't know. Y'all, don't you feel like you look smarter? But really, is this that hard? No, it's not. I mean, like, show this. I'm telling you, like, show this cool chi-squared symbol to your parents. They'll be like, I don't even know what that means. Show it to my calculus kids. They don't know. Show it to John.